name is Cam, and this is Physics 2211, Lab 4. The purpose of this lab was to observe the motion of a mass tied to a spring and compare it to the model made for prediction for the conservation of energy and oscillation period. For the experiment, we observed the motion of a mass attached to a spring oscillating and swinging at the same time. We either recorded or used a pre-made video to track the motion and plug the data points in, ignoring time, into an Excel sheet and imported it into GlowScript. We compared the code made to predict the spring's movement to the tracker movement and report the results. These were some of the principles we used: the energy principle, gravitational potential energy, Newton's second law, spring force, the velocity update, and a position update. These are the formulas for the principles mentioned in the previous slide, where you can see the energy principle, gravitational potential energy, spring force equation, velocity update, and position update formulas all in one spot. This is an overview of the tracker data. These are the conditions for our experiment. We put everything in the system, including the spring, earth, and the object tied to the end of the spring, and left nothing in our surroundings. Our mass was 0.402 kilograms. Our position was negative 0.103 with negative 0.092 in the y component. Our initial velocity was 0. Our gravity was negative 9.8 for our acceleration. Our spring constant was 5.82 Newton meters, and our relaxed length was 0.0231 meters. And for our time, we had just around 9.5 seconds total. This slide just shows some of our coding that we used for our prediction model. And here's our comparison. So for the similarities, the model and the lab both oscillate at a similar rate. As you can see, the graphs go up and down around the same points in the graph, especially towards the start. And for our differences, the graphs are slightly offset from each other, and the accuracy slightly decreases as time goes on. As you can see, the later ends start to deviate a lot more from where it was at the start, where they're pretty similar. For potential errors, we have rounding, missing the center of mass when tracking throughout the frames, and potentially making a mistake during the coding that could set our variables off. Discussion: the energy principle holds true in this lab. If you add all the energies together, it will equal 0 for each part of the graph, and the total energy of the system never changes, so the energy principle is consistent. The oscillation period for the x position of the data is different from the y coordinates oscillation period. The changes in the period could be solved or caused by inconsistencies in tracking. A small deviation in each oscillation within the tracking process can cause a large difference over the course of the whole graph. And the estimation for the average period for the x component was 1.476 seconds, and for the y component it was 1.293 seconds. To conclude, even through the motion of springs, all energy in the system will be conserved when no outside surroundings directly affect the motion of the spring system, as shown through this lab. Thank you for watching.